Today's experiment is about Experiment 9, Sieving and Plastic Limit by Atterberg method, performed by Group 4 of CE14E2, which consists of Galarrita, Guiling, Gulay, and Honculada.
This procedure covers the method of sieving and plastic limit by Atterberg's method in accordance with ASTM D4318 and AASHTO T90. Using the Atterberg limits experiments, it is possible to pinpoint the moisture levels about which fine-grained clay and silt soils transition from firm to semi-solid to plastic to liquid phases. To predict how soils will respond to applied pressures and shifting moisture conditions, geotechnical engineers must evaluate soils that are designed to support buildings, roads, or other factors. In order to clearly characterize the boundaries between these states solid, semi-solid, plastic, and liquid of clay and silt, Atterberg limit tests are important for identifying the moisture level at the sites where the physical changes occur. The behavior, reliability, and strength vary noticeably at each level. The test results, unrelated indices, are used to predict how soil layers, dikes, and roads will behave as well as to design the foundation of buildings. The measurements also identify expansive soils and forecast settlement by determining soil permeability and shear strength. The materials and lab equipment to be used are soil, distilled water, sieve number 200, beaker, 3 moisture cans, evaporating dish, spatula, triple beam balance, mechanical siever shaker, and laboratory oven.
We prepared the soil in the laboratory by crushing it in order to prepare it for sieving. We used the number 200 sieve and the sieving motor for sieving the soil, in which Sir Johan assisted us. We measured the mass of the 3 moisture cans and labeled them. For trials 1, 2, and 3, the mass of the moisture cans are 0.0123 kilograms, 0.0117 kilograms, and 0.0123 kilograms respectively. We then put exactly 30 grams of soil in the moisture cans. We pour the distilled water into the soil. We keep adding distilled water until the consistency of the soil can be rolled without sticking into the hands. We form the soil into ellipsoidal mass. We roll the soil into our hands on a non-absorbent surface. The thread of the soil shall be deformed in order to reach a diameter of 3.2 millimeters. If it reaches 3.2 millimeters of diameter, break it into smaller pieces. Knead the smaller pieces and reform them into ellipsoidal mass. We gathered and placed the smaller pieces into the container. We weighed the can that contained the wet soil and recorded it. Repeat steps from forming the soil into ellipsoidal mass to gathering and placing it into the container at least twice. We placed all the containers into the laboratory oven for at least 16 hours. After 16 hours, we got the samples and we weighed each of the can that contains the oven-dried soil.
In the experiment, we have a total of 3 cans. Each was weighed and their weights are 0.0123 kilograms for trial 1, 0.0117 kilograms for trial 2, and 0.0123 kilograms for trial 3. We then weigh the can and the sample that are wet. For trial 1, the weight is 0.434 kilograms, trial 2 is 0.0441 kilograms, and the last trial is 0.0452 kilograms. These samples were oven dried for 1 day, and after that, the samples were weighed again. The weight of the oven dried sample plus the can are 0.0386 kilograms for trial 1, 0.0379 kilograms for trial 2, and 0.3845 kilograms for trial 3. After collecting this data, we then proceed to calculating the mass of pore water, mass of soil solids, and moisture content. We got the mass of pore water by getting the difference between wet weight of can plus the sample and the dry weight of can plus the sample. The mass of pore water is the following: 0.00448 kilograms for trial 1, 0.0062 kilograms for trial 2, and 0.00675 kilograms for trial 3. Next to this is the mass of soil solid. We got this by getting the difference between dry weight of can plus sample and the weight of the can. The mass of the soil solid is the following: 0.0263 kilograms for trial 1, 0.0262 kilograms for trial 2, and 0.02,615 kilograms for trial 3. For the moisture content, the formula for it is weight of water over the weight of oven-dried soil or sample multiplied by 100 after. The moisture content is as follows: 18.25% for trial 1, 23.66% for trial 2, and 25.81% for trial 3. Lastly, we got the average plastic limit by getting the average of the moisture content, and the average plastic limit is 22.57%.
While our group performed plastic limit by Atterberg method, we discovered that we had different behaviors of soil while making the threads. Because although we had the same soil samples and amount of water poured for about 5 ml, there are biases in how we roll, how fast we perform the threading, the decreased outside factors such as air heat, errors in mixing, and how moist our hands were. There are also no 1/8 inch or 3.2 mm rods present in the laboratory as a calibration tool to have uniform soil threads. Thus, this is also prone to error because there were sub 3.2 mm threads made. This is seen in our results wherein the plastic limit of trials 1, 2, and 3 were different for about 2% to 7%. The inconsistency in plastic limits is due to the difference of the mass of wet soil minus mass of dry soil. Our data in moisture content we've achieved is convincing enough because it didn't reach the 30% as it was the class threshold for the start of the liquid limit test.